Hello everybody, it's your friend Daniel here and welcome to another tuition video, where in this video we're going to be covering GCSE Physics Higher Tier, Paper 1, and we're going to be doing the 2018 paper. So starting off straight away with question 1. Figure 1 says a student walking on a carpet. The student becomes negatively charged because of the friction between his socks and the carpet. Explain why the friction causes the student to become charged. And what happens is electrons, which as you may know are negatively charged, they move from the carpet to the student, causing the student to then become negatively charged. And if you've ever been static shocked, this is what causes it. Then moving on to 1.2, the student's head is represented by the sphere. The student is negatively charged. The arrows show part of the electrical field around the head. And we're asked to draw 3 more arrows to complete the electrical field pattern. And what you need to do here is you just need to draw 3 arrows perpendicular to the sphere going into the sphere. And then we're asked why the negatively charged student touches a metal tap and receives an electric shock, and we're asked to explain why. And what happens is because the student is negatively charged, because the electrons from the carpet, there is a potential difference between the student and the tap, which is not charged, which causes the electrons to transfer from the student to the tap, which earths the charge, electrocuting them. And then we're asked, some carpets have thin copper wires running through them. The student is less likely to receive an electric shock after walking on this type of carpet. And we're asked to suggest why. This is due to the copper having a low resistance, so charge would no longer build up on the student from the carpet, leading to there being no potential difference between the student and the tap. So how this is all working is that electrons are transferring from the carpet to the student, and then the electrical shock, is being caused when the electrons transfer to the tap. And with the carpet having a low resistance with the copper wires, there is no charge that is being transferred to the student, so they aren't getting electrocuted when they touch the tap. Now moving on to question 2. A teacher used a Geiger-Müller tube and counter to measure the number of counts in 60 seconds for radioactive rock. The counter recorded 819 counts in 60 seconds. The background radiation count rate was 0.3 seconds per count. Calculate the count rate for the rock. And what we need to do, we just need to do 819 divided by 60, which is 13.65 counts per second. And then what we need to do is we need to take away the background radiation, which as we are given in the question is 0.3 counts per second. So it's 819 divided by 60, which gets you 13.65. And then you take away 0.3, which leaves you to a final count rate of the rock being 13.35 counts per second. And then with 2.2, we're told a householder is worried about the radiation emitted by a granite worktop in his kitchen. 1 kilogram of granite has an activity of 1,250 becquerels. The kitchen worktop has a mass of 180 kilograms, and then we're asked to calculate the activity of the workshop in becquerels. And what it is you just multiply them, and you get an activity of 225,000 becquerels. Then moving on to 2.3. The average total radiation dose per year in the UK is 2 millisieverts. Table 1 shows the effect of radiation dose on the human body, and we're told that 10,000 millisieverts is immediate illness, death within a few weeks, 1,000 is radiation sickness, and 100 is the lowest dose with evidence of causing cancer. The average radiation dose from the granite worktop is 0.003 millisieverts per day. Explain why the householder should not be concerned about his yearly radiation dose from the granite worktop. And then we're told 1 year is 365 days, which is actually rather nice. So if the daily dose is 0.003, then the yearly dose is going to be 0.003 times 365, which gets you 1.095, which is significantly lower than the lowest dosage with evidence of causing cancer. And then we're told bananas are a source of background radiation. Some people think the unit of radiation dose should be changed from sieverts to banana equivalent dose. And we're asked just one reason why the banana equivalent dose may help the public be more aware of radiation risks. And this is rather simple. People are able to compare the risk of radiation to the radiation dose of eating bananas. So, for example, if we're told having a granite worktop in your house is equivalent to eating 3 bananas, 3 bananas is a lot easier to understand for any average person than 0.003 millisieverts. Unless you're doing like high level physics, you won't know what a millisievert is. Okay, now moving on to question 3. A student investigated how the resistance of a piece of nichrome wire varies with length, and we're shown parts of the circuit that the student used, and we're asked to complete figure 3 by adding an ammeter and a voltmeter. And as you remember, voltmeter goes in parallel with the thing you're measuring, and an ammeter goes in series. So that's what I've done. The voltmeter is a little circle with a V in the center, and an ammeter's a little circle with an A in the center. Okay, now moving on to question 3.2. Describe how the student would obtain the data needed for the investigation. And the investigation is the one the last question was on, where they wanted to work out the resistance of a nichrome wire. And what they need to do is they need to measure the length of the wire and then measure the current and potential difference for that length using the circuit setup I showed above. And then they need to vary the length, measuring the voltage and current for each length, taking repeat readings. And then you calculate the resistance for each length using the formula resistance equals potential difference over current. And then you proceed to plot a graph of resistance against length. And one major hazard of this, because it asks for a hazard in the investigation, is that a high current which could cause the wire to overheat and burn someone if they touch it. And to prevent this, it's important to use low currents. Honestly, that's not that bad for one of the first major 6 markers in this paper, and let's move on. Why would the student switch off the circuit between readings? Why would that improve the accuracy of the student's investigation? And this is due to the temperature of the wire not changing. Because if they leave it on, the temperature of the wire would increase, which would lead to increased resistance, messing up the investigation, because the wire would have to have needs to have a constant temperature. And for 3.4, the student uses a crocodile clip to make connections to the wire. They could have used a piece of equipment called a jockey. Figure 4 shows a crocodile clip and a jockey in contact with a wire. How would using the jockey have affected the accuracy and resolution of the student's investigation? Now what you notice is the crocodile clip is taking up a larger length, while the jockey is taking up a smaller length. So you can, using the jockey, you get the length of the wire more accurately. And you can see with the options here, it would lead to the accuracy of the student's result being higher, and the resolution of the length measured would be higher because it has a thinner point. Now, on question 4, figure 5 shows a cyclist riding along a straight level road at a constant speed. I'm asked to complete the sentences. As the cyclist rides along the road, the chemical energy stored in the cyclist's body decreases, and the speed of the cyclist is constant when the work done by the cyclist is equal to the work done against energy resistance. Because for their speed to be constant, the work done pushing them forwards would have to be equal to the work done pushing them backwards by air resistance, leading to there being no resultant force and them keeping a constant velocity. Then for figure 6, we're asked how the speed changes as the power output of the cyclist changes, and we're asked to write down the equation that links power, time, and work done, and you can just use your formula book for this. Power equals work done over time, because you remember work done is energy. And then for 4.3, calculate the work done by the cyclist when his power output is 200 watts for 1800 seconds. So 200 equals work done over 1800. Work done equals 200 times 1800, and you get a work done of 360,000 joules. And then moving on for 4.4, we're asked to calculate the percentage increase in speed of the cyclist when the power output changes from 200 watts to 300 watts. And then what you can see here for 200 and 300 watts, I just drew up the graph and went across. For 200 watts, it's 9.5 meters per second, and for 300 watts, it's 11 meters per second. And the formula for percentage change is just a math thing. It's the change over original times 100. So you can see the change between 9.5 and 11 is 1.5. So it's 1.5 over the original speed, which is 9.5 times 100, and that gets you a percentage increase of 15.8%. and we're told the maximum speed a cyclist can travel on a level road is 14 meters per second. How does cycling uphill affect the maximum speed of the cyclist? The maximum speed of the cyclist would be lower because the maximum power output would stay the same, but additional work would have to be done against gravity. Now, as I said earlier, the cyclist is moving at a constant speed, their max speed, when work done by the cyclist is equal to work done against their resistance. However, if they're cycling uphill, they also have to do work done against gravity. So that additional work done against gravity means that they move at a slower speed. Now 5.1, just choose answers from the box. The current through an ohmic conductor is directly proportional to potential difference across the component, provided that the temperature remains constant. And for figure 7, we're shown a potential difference graph of a filament lamp, and we're asked to explain how the resistance changes as the potential difference across it increases. The current increases when the potential difference increases, which causes the temperature of the filament lamp to increase, causing the resistance to increase. Now, as you may know, if you do V equals IR, you can rearrange that to get R equals V over I, which means that resistance is actually 1 over the gradient of this graph, which means the flatter the graph is, the higher the resistance is. And that's how you know the resistance is increasing, because the graph begins to flatten out. Many households are replacing their filament lamps with LED lamps, which are more energy efficient. And for some reason, I do not have the answer to this. But more energy efficient, it just means I'll type it with you guys. Let's do a group exercise. Yippee. More energy efficient means that more of the total energy input is converted to useful energy output, which in this case, more of the energy put into the LED lamp, more of the electricity put into the LED lamp, would be turned into light. Don't know how I missed that question. Anyway, moving on. A light-dependent resistor is used to turn on an outside lamp when it gets dark. Part of the circuit is shown in figure 8. The light intensity decreases. What happens to the potential difference across the LDR and the current in the LDR? Well, as an LDR has a decreased resistance when light intensity increases. So a light intensity decreasing would lead to it having a high resistance. And what would a high resistance do? It would mean that the potential difference would increase and the current would decrease. I cover all of this LDR, different circuit stuff in my video, which explains every circuit symbol. So I'd recommend go watching that if you struggle with this topic in particular. And then for 5.5, we're asked what the resistance of the LDR is when the potential difference across it is 4. And it's 1,000 because the potential difference is shared in proportion to resistance. So, for example, if this has a potential difference of 4, because it adds up to 12, this must have a potential difference of 8, which means because the potential difference is half of what it is across the resistor, the resistance must also be half, and half of 2,000, as you guys know, is 1,000. And then for 5.6, we're asked to calculate the current through the LDR when the resistance of the LDR is 5,000 ohms. And we just used the V equals IR formula. 12 equals I times 7,000. I equals 12 divided by 7,000. So I equals 0.0017 amps. Honestly, so many of the math questions in physics are just very simple if you practice rearranging formulas. So if you get really good at rearranging formulas in regular maths, it will just make physics so much easier. Moving on to question 6. Smoke alarms contain an alpha radiation source and a radiation detector. Figure 9 shows part of the inside of a smoke alarm. The smoke alarm stays off while alpha radiation reaches the detector. Why does the alarm switch on when smoke particles enter the plastic casing? And how it works is that when the smoke particles enter the plastic casing, they absorb the alpha radiation, stopping it from reaching the detector. And when it doesn't reach the detector, the fire alarm goes off. And then we're asked, why is it safe to use a source of alpha radiation in a house? It's not very penetrating, and it has a very short range in air, so it's not actually going to be able to reach you. And if it does reach you, it's going to be very negligible. And 6.3, the smoke alarm would not work with a radiation source that emits beta or gamma radiation. And this is because beta and gamma radiation will penetrate the smoke, and thus the detector will not detect a change in the camera rate. I don't know what's going on with my PDF work today, guys. Still getting all the answers you need, though. Anyway, 6.4. Figure 10 shows how the count rate detected from the radiation source in the smoke alarm changes with time. The smoke alarm switches on when the count rate falls to 80 counts per second. Explain why the radiation source inside the smoke alarm should have a long half-life. And this is due to a long half-life, meaning the count rate is constant, approximately constant, and until 1.9 half-lives, the count rate is above 80 per second. So if you have a half-life of only like a month, it will only take 1.3 months until the count rate falls below 80 per second, leading to the fire alarm going off constantly when it shouldn't be. Now on to 6.5. Figure 11 shows a patient who has been injected with a radioactive source for a medical diagnosis. It's actually really cool. One of the cool things that you learn about in GCSE Physics. Explain the ideal properties of a radioactive source for use in medical diagnosis. It should have a short half-life and a low ionizing power, both of which meaning less damage is done to the body, and it should also be highly penetrating, so the radiation can escape the body and be detected outside of it. And how it works is like the radiation can sort of cluster in parts of the body. So like radiation could sort of like cluster in your kidney, and they can detect the radiation in your kidney to see if it's working properly. It's really cool. Okay, then for question 7, a student investigates how the pressure exerted by a gas varied with the volume of the gas. And figure 12 shows the equipment that the student used. A pump was used to compress the gas in a tube. As the volume of the gas decreases, the pressure of the gas increases. The student only recorded one set of results. Give 2 reasons why taking repeat readings could provide more accurate data. And this allows you to calculate a mean, which improves accuracy, and it also allows you to identify and remove anomalies. Then figure 13 shows the position of the student's eye when taking volume measurements. And for 7.2, we need to explain what type of error would be caused if the student's eye was not in line with the level of the liquid in the table. And it would be a parallax error, which is a random error because eye position relative to the liquid not be the same. And I've drawn a quick diagram up here. If the student was looking up at an angle, they'd see it, the water level as being higher than it would be, and if they're looking down at it, they'll see the water level as being lower than it should be. You don't need to draw the diagram in the slightest. It just often helps my students see physically what the actual issue would be if you did that. Now for 7.3, if the gas is compressed too quickly, the temperature of the gas increases. Explain how the temperature increase would affect the pressure exerted by the gas. And the temperature increase would increase the pressure in the tube, because a higher average temperature would mean a higher average kinetic energy of the particles, because temperature is just a measurement of how much kinetic energy a particle has. Of course, that doesn't mean something at 0 degrees has 0 kinetic energy, because scientists use the Kelvin scale, which is absolute, which means that 0 Kelvin means that there is 0 kinetic energy in a particle or a group of particles, but 0 Celsius doesn't mean that. Zero Celsius is just, well, it's not arbitrary because it's linked to water. I'm going on a side tangent here. Basically, higher temperature, higher average kinetic energy of particles. 7.4. One of the students' results is given below. A pressure equals 1.6 times 10 to the 5 pascals, and a volume equals 9 centimeters cubed. Calculate the volume of the gas when the pressure was 1.8 times 10 to the 5 pascals. The temperature of the gas was constant. And you know that pressure times volume is a constant. So if you do 1.6 times 10 to the minus times 10 to the 5 times 9, you get 1.44 times 10 to the power 6. And then if you do 1.8 times 10 to the 4, 1.8 times 10 to the 5, which is the new pressure times the volume, you get also get 1.44 times 10 to the power 6. And then what you simply do is you divide 1.44 times 10 to the power 6 divide that by 1.8 times 10 to the power 5, and you get the new volume, which would be 8 centimeters cubed. I'm real issues with the PDFs. Okay. 7.5, figure 14 shows a person using a bicycle pump to inflate a tire. The internal energy of the air increases as the tire is inflated. Explain why. And this is due to the work being done on the air, so the temperature increases. And as you may know, a temperature increase leads to an increase in internal energy. Okay, now on to question 8. Nuclear power plants generate electricity through nuclear fission. Electricity can also be generated by burning shale gas. Describe the disadvantages of nuclear power compared with the use of shale gas to generate electricity. And I'll be honest, I just copied the points from the mark scheme here because they're very easy, and the mark scheme's formatting was actually good, which is a surprise from AQA. And this is due to advantages of nuclear power being that no carbon is emitted in the production of electricity, it doesn't cause global warming, and nuclear power doesn't cause earthquakes, all of which is bad and is quite often caused by fracking, with there being evidence that fracking does cause earthquakes. And what is the name of one fuel used in nuclear power stations? Uranium. You could also accept plutonium. Okay, now moving on to 8.3, which is to describe the process of nuclear fission. A neutron is absorbed by a large nucleus, which then proceeds to split into two smaller nuclei, which releases energy and gamma rays and 2 or 3 neutrons. With those 2 or 3 neutrons, then often going into other large nucleuses, causing them to split, which often leads to a larger chain reaction, although it doesn't ask that for the question. However, you wouldn't be penalised for writing it down. Then for 9, figure 15 shows a coffee machine. The coffee machine uses an electric element to heat water. The coffee machine has a metal case. Why would it be dangerous? For the live wire of the electric cable to touch the metal case. And this is due to there being a risk of electric shock if anyone touched the case. And then we're given the power output of it and the potential difference, and we're asked to calculate the current. And in your formula book, you have the formula power equals current times voltage. And you can just do 2,530 equals current times 230. And if you're good at maths, you'll notice that 2,530 is a multiple of 230, with it being 11. If not, just put it into a calculator and you get the current equaling 11 amps. And then we're given a rather, well, I say a rather hard 5 marker. The coffee heats water from 20 to 90 degrees Celsius. The power output of the coffee machine is 2.53 kilowatts. The specific heat capacity is 4,200 joules per kilogram. Calculate the mass of water that a coffee can heat in 14 seconds. So what we first need to do is work out the energy, and energy equals power times time. So which is 2,530 times 14. Which gets you an energy of 35,420. And then you just sub that into mass, sub that into the specific heat capacity equation, and you get 35,420 equals mass times 4,200 times 70. Then you get mass equals 35,420 divided by, in brackets, 4,200 times 70, and then you get the mass is just 0.12. None of the actual maths is that hard. All the struggle comes from being able to rearrange and plug equations in to actually get the marks. So if you're good at the maths aspect, I'd really practice rearranging the equations to try and maximize the marks you can get from this section. Okay, now for figure 10. Figure 10 shows a wind turbine. At a particular wind speed, a volume of 2.3 times 10 to the power 4 meters cubed of air passes the blade each second. The density of air equals 1.2 kilograms per meter cubed. Calculate the mass of air passing the blade in seconds, and density equals mass over volume. So mass would just equal the density times volume, so you just do 1.2 times 2.3 times 10 to the power 4, and you get a mass of 27,600. And then the power output of the blade is directly proportional to the kinetic energy of the air passing the blade each second. Describe the effect on the power output when the wind speed is halved. Now the more obvious part, I've written the more obvious part at the end. If the wind speed is halved, kinetic energy is decreased by a factor of 4, since kinetic energy equals 1 over 2 mv squared. However, it's not just decreased by a factor of 4, because the mass of the air that passes through the wind turbine is also halved, since less air is passing through it due to the wind speed being halved. So it actually decreases by a factor of 8. Then for the last question, at a different wind speed, the wind turbine has power of 388 kilowatts. The mass of air passing the turbine each second is 13,800. Calculate the speed of the air passing the blades each second, and we're asked to assume the process is 100% efficient. So what we just need to do is we need to do the kinetic energy formula. Because it's 1 second, we don't need to convert the power into energy. We can just use the power because the power is energy per second. So we convert 388 to 388,000, and then we're asked to calculate, and then we just plug that into the formula, rearrange it to get v squared equals 56.2 and v equals 7.5. Anyway, that's the end of the video. If you enjoyed it, make sure to like and subscribe, and I'll see you next time for more content.